Hey, you 11. Really hoping that you guys are able to join me today. We're going to be in our last lesson. Sorry, I'm just trying to get my other laptop. Remind me tomorrow. I'm just trying to get my other laptop. Let's see if I can find. There we go. There's my live. Oh, pause. I like it. Okay. So last lesson, which was yesterday, we looked at titration methodology, and we covered this bullet point sequence of points that you guys need to know. So we were looking at how we need to be able to collect our equipment, and of course the questions regarding those are usually they give you diagrams of the equipment and you're expected to be able to name those pieces of equipment, followed by then you fill the burette with an unknown solution. You can take a reading at that point if you want. Lots of people like to put that at that stage, but you don't have to. You can put it at the end if you want. But fill your burette with an unknown solution. Using a graduated pipette, add 25 mils of an unknown solution to a conical flask. Hey, Anch. Hey, Julian. Thanks for coming, guys. Really, really great to see you guys that you're here. Thanks for coming. So then you're using your graduated pipette and pipette filler. You add 25 mils of your unknown solution to a conical flask. You then add 3 drops of your indicator. You then add the acid or alkali, whichever one it is, from your burette. You add quickly at the beginning and then drop-wise near the end point, and you stop when you see a permanent color change. And you take a reading at the start and at the end. That's the methodology that we discussed in terms of a titration last time. Next lesson, when you're actually in school, we're going to actually have a go at doing that practical. So watching the video that I showed you guys in lesson is useful because obviously we haven't been able to do this and have a bit of a hands-on lesson on titrations yet. Hey, Hiba, thanks for coming. It's great to see you. And today I'm looking at the calculations that you guys are going to be doing and the data that you're going to have collected. By the way, I can't make that blue box around my face vanish, and it's driving me crackers. So today we're going to be having a look at actually looking at the data and what the questions look like from a GCSE paper. So, okay, so we're doing titration calculations today. See, I'm just setting up my laptop so I'm able to write on it. So there are a couple of learning objectives that I want to do today. The first learning objective is to be able, it's able to recognize titration, I don't know why I capitalized it, titration questions. Next one is understand titration data. Understand titration data. And then the third one is to be able to use data to complete titration calcs. To complete titration calcs. Okay. Okay, now what I've done is I did quickly realize that the importance of actually seeing these real exam questions is really important. So I went online and I went on to tutormyself.com, which is a fantastic resource because if you go to the revision section, show you where I got these from. It's just a nice reminder for you guys. If you go to Tutor Myself, and the great thing about this website is it's only for GCSE Edexcel chemistry, which is so awesome. I do love what this guy has done. And if you go to the specification, what you can then do is, actually, do you know what? I actually did this on physics and maths. I've just realized that I've done this on physics and maths. But if I scroll, there's the acid-base bit. There it is, acid-base titrations. And if I go click on that one, and you actually click on that triple only, describe how to carry it out. We then see questions, and if you then click on them, of course, it then takes you to your Edexcel paper directly to those questions, which is really, really nice. So, and I've taken a few of these, and I've then put them into my lesson. Here's the data. They're expecting to see whether or not you can take readings, and I've put some of these questions then, of course, onto my document to enable us to be able to actually discuss them and talk them through. So, okay, let's start from the top. This is question 3. Now, the reason why I've skipped through to question 3, if anyone's wondering, is because this booklet that I've taken actually from Physics and Maths tutor actually includes another topic called enthalpy change, which we are doing after acids and bases. So I'm skipping down to question 3, which is the first titration question. So it says, a student carried out a titration to find the concentration of some sulfuric acid. A supply of dilute sulfuric acid, sodium hydroxide solution, apparatus suitable for carrying out titration, and phenolphthalein indicator. So the first thing it says, name the piece of apparatus. So as I said, these are where the apparatus questions come in. Name the piece of apparatus that is used to add the sodium hydroxide in step number 1. So immediately we look at step number 1 and we realize that it says 25. This is a fixed, it should say centimeters cubed, but I don't know why it's been deleted, but it has. So 25 centimeters cubed of sodium hydroxide to a conical flask. So our piece of apparatus is going to be our graduated pipette, our super smart pipette, just come out of university. Fantastic. So our graduated pipette, I think actually, and in fact I know that on Edexcel, they do allow you to just simply say the word pipette. And by the way, I've just suddenly realized, I just want to do a quick check and make sure I haven't muted my microphone. Nope, that's all good. Microphone is all good. So my graduated pipette is going to be used because it was that fixed volume and it's going into the conical flask. Next, what color change of phenolphthalein indicator will there be in step number 4? Well, we know that if we draw the picture out, we know that we've just added 25 centimeters cubed of an alkali, sodium hydroxide, has just gone in here. So this is NaOH. We know it's an alkali, and phenolphthalein, I link back to your universal indicator, and alkali is purple, and phenolphthalein begins with the same letter, but in this case, we're going to see it be pink at the beginning. And what's then going to happen is we are then going to add the sulfuric acid from my burette until we see a permanent color change. And we're going to see it go from pink to colorless. So there's that one, so that's B. Next, why is it better to use phenolphthalein indicator rather than universal? So we chatted about why you can't use a universal indicator when we did our lesson in the library. So we can't use universal indicator because it has multiple color changes. That's why we can't use that. We'd have to be aiming for green, but there'd be multiple greens. So we can't use this. Phenolphthalein is better because it has one single color change. And it is also, I always like to say both, it has one single color change and the color change is very distinct. To go from colorless to pink or pink to colorless, that is a very clear, very easy sign to know when to stop. So this is an obvious, notice I don't put a clear color change because of the word clear. I'm going to say obvious color change. I'm going to put CC, color change. Obvious color change. So you know when to stop. It has a very clear end point. And by the way, the word end point is a term in titrations. So it's nice just to reinforce that. So a couple of bullet points there. One color change, and it's a very obvious color change. I would always put both. The next one is reading a burette. So this, of course, I haven't really been able to teach you guys yet because you haven't really seen them. But you can do almost everything over a webinar. If I do a quick search for burette reading and I click images, I want you to see something that's kind of important here. And that's right there. So that's a really lovely picture and it's great quality. And you can see what I'm aiming for very clearly, which is the fluid, the solution that is in my burette is not level. It has a very distinct shape to it. And that is, I'm just going to draw on it here. And that shape you can see, I'm sorry, hang on a sec. The shape is there. And the shape is curved like this. Now that curve is very important. It is given a name and it is called the meniscus. Meniscus. It's called the meniscus. And the reason why it does this is because the solution, water is a very sticky substance. It's exactly the same, it's the same thing happens when you put a drop of water onto a table. Water is sticky. It doesn't want to spread out. It will stick to itself and it sticks to surfaces. And what it's doing is it's sticking to the walls of the burette. And what that means is it actually pulls it up. It's actually called the capillary effect. It's a biology term, really. It's where you come across that at GCSE. It's called the capillary effect, or capillary, either one. I prefer capillary myself. And you can see this, that it's pulling it up the walls of the burette, which means that the solution has to be read from a very clear point, which is you have to read it from the bottom of the meniscus. The reason being is the tube, the burette, is designed to take into account this small amount that's climbing the walls. So you always read it from the bottom of the meniscus. And in this case, it's that little blue line right there. So that line, so it's the reading, and you also, and this is another important point, you always read a burette top down. This is an unusual thing to happen, because most of the time, if you see something like a thermometer, you read it from bottom up. But with a burette, you read it top down. And the reason for this is because when you fill a burette to 0, and that's then full, and you drain the liquid out of it, and then and of course the liquid drains down as it moves down, as it slowly moves down the burette, as it empties out, you then take the reading top down for where the solution stops, so you know the amount of fluid that you have added. So it's quite an unusual thing. And so there's the test from your GCSE exams. You can even see that they have tried to show the meniscus. They've tried to show the curving edges of the fluid. They haven't, in this particular case, they've actually been relatively nice, and they've made it, they've still given it this level section. I've seen others, and it'll be interesting to scroll through this document to see if there are others that have a real curve on it. So in this case, you can see that the line here, I'm going to try and shrink my pen, I think, because it's way too fat when I'm this zoomed in. So that, we're going to read it top down. So this is 2 point, because you can see that the main 2 and going up to 3. This here would be 2.50. That would be what that would be, 2.50. Notice the extra decimal place. But this case, it is 2.10, 2.20, and our reading there is 2.30. Now, the habit, of course, that students have, and here's, of course, they're asking you to fill in the data. They're going, if they ask me what the reading was before, there you go. So notice they've done something really clever there. It's everything at GCSE is a trap, everything. Notice that in the diagram, we always know that because of books, we tend to read things from left to right. And they've done before and after. This makes total sense. Look at the data. It says, give the reading after. And lots of students will write down the before in the after box, because simply they're looking at it from left to right. So it's an obvious trap, but students do fall into it. Don't be one of them. So they want the after one first, followed by the before. Now, at this point, I will mention the second decimal place, because the habit is the before one for students to write down 2.3. And I understand this because the reading is 2.3. However, a burette is able to read to 2 decimal places. However, that number, the number is either a 0 or a 5. And I'll explain why. The reason being is, if we just take these 2 points there for an example, this would be 23.123 and 23.40. Notice that there is no scale. There is no scale. This is as thin as I can go. There is no scale between those marks. What that means is you cannot give oh, 23.2, you can't do that because there are no lines to give you a real reading. However, you can tell if it's between them. What that means is if your meniscus lies between 2 points, you will give that as 24.15. So you can, this second decimal place must be there, and it will either be a 0 or a 5. And they usually ask you to take these two readings. One of them will be a whole number to check to see if you remember to include the decimal, which everyone forgets, throw away the mark. And the next one is to see whether or not students are going to do 24.1, and then they're going to put a crazy number in here like 3. But it's never that. It's always going to be a 5. You're reading it top down, and it's either a 0 or 5 on the decimal. And then the volume added, of course, is relatively straightforward. You take away the start from the latter, and so we're going to end up with, and by the way, yes, I am doing this on a calculator. I could do it on in my head, but I'm not going to, because I'm never, ever wanting to drop any marks for silly calculation mistakes. So that's 24.15 minus 2.30, and I get 21.85 centimeters cubed. So nice and easy, but do you know what? It always amazes me at how many students can't do those questions. And I think it's more of an exam panic, and also because you guys class this as easy, and so you tend to make mistakes. This is one which I always say to students, don't rush it. It is easy. They are 3 marks, but don't rush it. Otherwise, you may make a mistake. I want to see if there's another one in this booklet. There may be. Let's see if we can find one. Oh, no, there isn't in this particular booklet. Do you know what? I wonder if I can find another one from an actual exam paper. I went to here. Let's have a look at this. There you go. Okay, folks, so this is just another one. You can see how they've flipped it over. So I've now got 3 people who are in the classroom. I'm going to put this out to Ange, Julian, and Hibber. I'm also going to see if I can time you guys on this because I'm such a nerd as that. So I'm going to say, there we go. Oh, I've just had Iris just turned up, which is great. I'm sorry I'm late. That's okay. Don't worry about it. So question to Ange, Julian, Hibber, and Ira. What is the reading before it? Sorry. What is the reading in the before one, please? Off you go. I like it. So I've got Ange's answer. So I'm going to now snip this, and you know what? I'm going to now check his answer. It's going to take a while. There you go. It's taking us time. There we go. So we read it top down. So that reading here is 2.12. Right, 2.2, and it is between the line. And well done, Julian. That's spot on. Can you now give me the after reading, please? Great job, Ange. Look at that, Ange. You're absolutely on this. First person there. And look, it's really nice. Okay, Hibber and Ira. Ira, you have absolutely every reason to get it wrong. Hibber, you have no excuse. You must remember to include that 0. Yeah, it needs to be there because we know that it's then going to be on that line. So top down, so it was 23.12345.6. It is on the line, so you must include that 0. Cool. And you know what? Isn't that lovely that I said students think it's easy, so they rush it and they write down the wrong answer. So Hibber, that's a really good example of how easy it is to make that mistake. in your exam, it happens a surprisingly large amount of the time. So don't be one of those people. Do try and remember. It's recognizing the trap. Okay, let's go to the next bit. Okay, right. So now I actually gave you guys your method and your 6-mark method. There is one more point to that method, but I don't often include it. Some students like to include it. It's technically not necessary to include it in every question, but also, whenever we do a titration, we always do it multiple times. So we repeat it. So if you follow my method that I gave you last lesson, we have burette, fill with unknown, fill with unknown. Next, we then had use graduated pipette to put 25 centimeters cubed of known in conical. Add 3 drops of indicator. Add acid or alkali from burette. Quickly at first, then dropwise at near endpoint, followed by take a reading, read, start and end, volume, and the final bullet point. There's your major 6 marks. There is another bullet point which you can say, repeat process until, now this is really A level, repeat process until concordance. The word concordance means results within 0.1 centimeters cubed of each other. Now that, by the way, that there is A level. Check out the GCSE adaptation on the question, 0.2. So they allow you a little bit of leeway on your titration skills at GCSE. So let's now have a look at their data. So they've done this 4 times. The first time, they added too much. Surprise, surprise, this is normal. This is called the rough titration. It's called the rough. It's because the first one, you always do what's called an overshoot. You always add a bit too much. So you do it again. The next one, he's added less. He's got better. He's got closer to the true answer. And then the next 3 are all pretty similar, but 2 are more similar than the others. And it's these guys. So those 2 there, because this is volume of acid used, they've done the maths for you. Yeah, this minus that, this minus this number, this minus this number, this minus this number, this minus this number. And this is the volume we added, vol added. So now we realize that 2 of the results are within 0.2 of each other. So I can now add a tick and say that and that is the correct result. And I'm now going to work out an average. So this is the first stage. If I go back to my learning objectives, my learning objective said to recognize titration questions. Well, most of the time they tend to say that in the question. And also you tend to see these pieces of equipment appear. We tend to see these readings off burette being asked. So that's relatively straightforward. And I think most people get it. Now we're starting to handle data, understand titration data. So we can make a couple of notes. Let's do a little bit of notes of titration data. So we're going to get a block of data. We're going to have repeat on our block of data that you can even draw in if you wish. We've got often the end vol in centimeters cubed, followed by start vol. Now, yes, by the way, lots of people are like, they're backwards. Why are they backwards? The reason being is it makes the maths a little bit easier. And then you have vol added. I'm not going to bother writing. I find it hard not to do it as bad practice if I don't. So vol added. And you do this, you repeat this 1, 2, 3, and 4 times. And what we realize is that we get these series of results and we have to pick the good ones. So we pick the data. So recognizing the data is important. And then we pick the data when we get, let's say we got 19.30, then we got 18.10, and then 18.15, and then 18.40. And we go, here are the two that are close. These are in concordance. They are concordant results. And now I'm going to work out an average. So if I go back to the question, the first thing they're going to do is ask me to calculate an average. There you go. Now that you have ticked the two results that are similar, that are closest, it says use your results to work out the average. So we now do 26.30 plus 26.40 and divide it by 2. Not a complicated process, very straightforward, and that I don't even need a calculator for, which is nice. And yes, if you have 3 of them, then you add those all together and divide by 3. This is not complicated. So, by the way, another common mistake, I'm switching from being a chemistry teacher to an exam prep teacher. Lots of students will do that and forget to write it on the line. Please don't be one of those students. It's very easy to do. Let's go to the next bit. So now that we've got an average, right? Okay, next question. The student uses a similar method to find the concentration of a solution of phosphoric acid, and they have given us an equation. We love equations. Why do we love equations? Because an equation gives us the mole ratio. So, the mole ratio is 3 to 1 to 1 to 3. But all I actually need out of that is the ratio between the acid and the base. So let's run this walk through our calculation. Calculate the amount in moles in the 25 centimeters cubed of the sodium hydroxide. So straight away, we're picking up, it's a moles calculation. We realize there are 3 moles equations. Grams over rams. Number of moles is C times V over 1,000. Or number of moles is V over 24. And we have to choose which one we want. Now, of course, this, is in a solution, which means we immediately pick C times V over 1,000. In the one in our notes, when the average is 0. Oh, what do you do? Julian, a really, really great question. Well done. You will simply round it. You would round it. Which way would you go? The answer is you'll never get it at GCSE. I always say that you should probably round down for a titration, because the answer should always be, but that's me knowing a bit more about titrations than perhaps you guys do. The answer is you would give it to whatever decimal place your calculator spits out. So I wouldn't worry. If it says give it to 2 decimal places, you would round it down rather than up. That's always my recommendation for titrations. So I would actually do 18.12. It's actually an interesting question, isn't it? Because the mathematicians would say you should always round up on a half. But in reality, because we know that in a true titration, you always overshoot by a small amount. So rounding down for titration is usually a better shout. But as I said, in your GCSE, it won't happen. And if it does, just give the real number that your calculator spits out. You would write down 18.125. Give the real one. So C times V over 1,000. I'll get rid of those other 2 equations. Now, by the way, I always say to students, good practice. You always write down your equation. Now add your detail. So number of moles is concentration. Oh, look, it's there. There's the concentration. So 0.180 multiplied by the volume. And the volume was 25 centimeters cubed, all over 1,000. Students often ask me why the 1,000, because we are getting given it in centimeters cubed, but the concentration is given in moles per dm cubed, so we have to do the conversion. Run that through our calculator, and yes, I'm not doing that in my head, I'm always going to use my calculator. 0.180 multiplied by No, sorry, I've typed that in wrong. 0.180 multiplied by 25 all over 1,000. And I get an answer of 0.0045, and I'm done. So there are my moles of sodium hydroxide. Right, calculate the moles of phosphoric acid. Well, this now immediately goes to my equation, because I have now got, let's zoom in on this. My pen's decided it's going to do it, it's just being slow. There we go. We now know that it's in a 3-to-1 ratio. I'm going to clean that up. This is in a 3-to-1 ratio. And I've just worked out that that is 0.0045. Well, if I want to go to phosphoric acid, I'm going to divide by 3. That's the whole point of the equation. That's why we balance. So I would write down NaOH to phosphoric acid is a 3-to-1 ratio. Right, therefore, 0.0045 divided by 3 gives me 0.0015. Just going to do that on my calculator. I know it's correct, but I'm doing it on the calculator anyway. Put your number in the box. And we're done. Next, now calculate the concentration. So now we go back to number of moles equals C times V over 1,000. Input your data. So we now know the moles of it. We've now got the phosphoric acid moles. We know its volume. We know its volume because we got that from the titration. Let's find that. Right. The average volume of phosphoric acid added from the burette is there. 28.3. So let's run it in. Number of moles, let's reorganize. Times 1,000. So move the 1,000 over. Bring the volume down, because that's what we've got. Gives us C. That there is always going to be worthwhile writing down. Input your data. 0.0015 times by a volume of 28.30 all over 1,000. No, hang on a minute. How easy it is to make mistakes. Times 1,000 over 28.30. Let's run it through. Times 1,000, the number's still on my calculator, divide it by 28.30, and I get an answer of 0.053 moles per dm cubed. And I'm done. So the whole, is he lagging, or is it just my Wi-Fi? Oh, I don't know. Hi, Sian. Nice to see you. Thanks for coming along. I don't know if I'm lagging. Yes, it's your Wi-Fi. Thanks for that. Yeah, it's nice to know that. I made a mess of my webinars yesterday at the beginning because YouTube have changed it and Google Hangouts is gone. So it's nice to know that it's all working okay. Right, let's do the next one. Now, this is still GCSE, and I always say to students, I can never, hi, I'm having YouTube problems. That's fair enough. Sorry, Sian, do the best you can. Use your data. So I always say to students, I can never teach you enough. And this question, number 4 here, is a question pulled directly out of an A-level paper, but not by me. This was on a GCSE exam, but they're using an A-level titration. The great thing is you don't need to worry. I'm teaching you chemistry to be able to use, and it's very straightforward, and it will still work. Let's have a look. The table shows the results. Titration number 1, 2, 3, and 4. Let's fill in those numbers and check our concordant data. So it says within 0.2, which means this is GCSE. If it was A-level, that would say 0.1. So let's check them. So 22.80, 22.1, that's not close enough. Oh, then it's got bigger again. It's too far. There it is. So our 2 results that are close enough for us to take our average are those 2. Notice the same process is running. They're getting you to look at the data and recognize which ones you're using for your average. Next, use your values to calculate your concordant, your average solution. 22.10. plus 22.20 divided by 2 gives me 22.15. Done. Next. Which is the most suitable piece of apparatus for measuring 25 centimeters cubed? Was the first one an anomaly? Ange, great question. Oh, Ange, you really do ask great questions. The answer is no, but yes. It was my rough. Whenever you do a titration, the first one, you always add too much. It's a result of just not, by the way, it's a result of not knowing how much you're adding to this, but also it's actually done on purpose. That requires a lot more conversation and really me having a burette in front of you to show you, and to show you why, when you do a titration, there are these like subtle steps. There are these subtle steps in terms of how you perform one that kind of make everything a little bit easier. And as I said, those really will be me when I'm doing it with you. And it will also be me taking you up to the A-level standard. And you just need to know that the first one tends to always be an overshoot. I will explain to you in lesson when we're doing the practical why that is. Okay, so which one? As soon as it says a fixed volume, 25, we're saying, isn't that interesting? The word graduated has vanished. And they've done this on purpose because everyone in this room will be going, it's a graduated pipette. That's what it is, it's a GPIP. But it's not in the list. Well, let's just go through them then. It definitely ain't a beaker, not accurate enough for 25. It's definitely not a gas because we're taking a solution. We definitely wouldn't use a measuring cylinder, not accurate enough. The only one there that we could choose is a pipette. So it's Edexcel doing a clever trick. They're gonna, let's just remove that word and see how many people we freak out. I've had students come out of exams saying they made a mistake and I wrote down the real one, and I'm like, no, they didn't make a mistake, they did it deliberately. So just be aware of it. So pipette is my choice. Oh, you've just seen me tick that box. Guys, that actually has caused a whole load of trouble for me in the past because I didn't know students were doing it. If it is a cross, you must put the cross in it. I know that is like ridiculous, but it needs to be crossed. Yeah, not tick. That's exam. That's me being an exam prep teacher. Right. So now we do exactly the same process. Calculate the amount of moles of potassium permanganate. Right. Number of moles is C times V over 1,000. Any students that's watching this that aren't in my class, I'm just going to mention moles equals MV. That is the original equation, and the capital M stands for molarity. You don't have to, and that's actually an old unit of concentration, and so I don't use it. I just use the letter C instead, totally allowed, and I divide by 1,000 in one go, just to make it really speed things up, but obviously recognizing that it's because the volume is in centimeters cubed. I'm just just for those people who are watching this who are not in my class. So let's lob in my numbers. Number of moles is concentration. Right, where's the concentration? It's in the data. There it is. And look, they're doing something. Look at the trap. They're deliberately missing off a number. It's just a 0. So concentration is 0.02 times by the volume. Right, what volume did they take? 20 centimeters cubed. Right, all over 1,000 because we're in centimeters cubed. Let's run this in. Of course, that's going to be more. It's going to be 4 times 10 to the minus 2 probably. Let's check. So 0.02 times by 20 all over 1,000. Oh, 10 to the minus 3. There you go. Oh, in fact, 10 to the minus 4. So 0.0004 moles. I like it. Next. In this reaction, 1 mole of potassium permanganate reacts with 5. They've told you the ratio. So even though the setting is something that you're massively freaked out by, you're going, I've never seen a potassium permanganate and iron 2 sulfate titration. It doesn't matter. It's all given to you. It's just designed to spook you, don't they? They've given you the ratio. Let's just make that a bit clearer for ourselves. KMNO4 is 1, and to iron 2 sulfate is 5. Right, who do I now have? I've just got the moles. Let's write that underneath, 0.0004. Right, how do I get to iron 2 sulfate? times by 5. So times that number by 5, and I now get 0.0002. So there's my answer. So what's fascinating is the fact that I've just got to check something here. It's a trap. I thought it might be. So I've just got the wrong answer, and I'll show you why. They dissolved their sample in 250 centimeters cubed, and they measured out a 25 centimeters sample. What that means is that is correct for the 25. So in fact, I haven't made a mistake yet. That is correct for the 25. There's the next question. So how many in 250 times by 10? That was the original that they took the sample out of. So that becomes 0.02. So that's in the total. Next. Is everyone with me? Hope so. Next, use your answer to calculate the mass in grams of these iron 2 sulfate. Right, well, hang on a minute. We've got that. They've even given us the MR. How kind of them. Number of moles is grams over rams. Reorganize. I've got rams and I've got moles. And they're asking for grams. Reorganize. Bring it up. Number of moles times rams gives grams. Right. Run my numbers in. 0.02 times by 152. So times that by 152. And I get an answer of the mass was 0.304 grams. Wow, that seems awfully low. Seems incredibly low. What have I gone and have I missed something here? I guess we'll find out. Right. It's very small. Considering we had 5.56 grams. Seems tiny. So, by the way, I'm now iffy about my answer, and I don't know if I should be. I think that I have done the maths correctly, but I feel like if it was 3.04 grams, that seems like a lot more sensible. But at this point, I want to check the mark scheme because I have doubt. If I was in an exam, I'd want to check this. So, did I do anything wrong? Did I type anything wrong in the calculation? I've got the concentration times by 20. That seems reasonable. Did I forget a 0 on that? Let's check it. 0.02 times by 20 divided by 1,000. Nope, that one is definitely correct. Therefore, times it by 5. Times it by 5 to get that one. That is also correct. Then times it by 10. That is also correct. And then reorganized. So that looks like the right answer. So I'd want to check that on a mark scheme. I really do. Do you know what? And I think I might. Let's see if I can find where I got that from. So I got that from, you have my attention for only 5 more mins. Too much chem and math. Thanks, Ange. That's hilarious. Okay, in that case, since Ange has just like completely done that to me, I'm gonna assume that I've made the correct answer. But let's go to the next one. In another experiment, 24 grams contained, they're doing empirical formula. This is water of crystallization, folks. So the total mass of that is 24.2. So I've got FeSO4.XH2O, and I have got is found to contain that much of iron 2. 15.2 grams of this guy. So therefore, if the whole thing weighed 24.2, 24 on first mark is going to be 24.2 minus 15.2. Oh, well, that's relative. Is that going to be 9? Yeah, 24.2. Still doing it on my calculator. 24.2 minus 15.2. Still doing it on my calculator. I just don't trust myself. Gives me 9 grams. Right, calculate the moles of water in it. So number of moles is grams over rams. So water weighs 18, of course. So 9 over 18, which is going to give me 0.5 moles. So 0.5 moles of water. Calculate the moles of iron 2. The iron 2 sulfate, so grams over rams over 152. Oh, isn't that a nice number? Which is going to be 0.1. So then I've got 0.1 of that. I have R, and then hence work out a value for X. I have got, so the moles of water is 5 times the size. Divide them all by the smallest. I'm just going to do FeSO4 dot X H2O. I've got 0.1 moles of that, 0.5 moles of that. I have 5 times the amount. Divide them all by the smallest. This is empirical. And I get 1 and 5. So my answer for X is 5. Answer's right. It's been 45 minutes. I've actually got to the end of my booklet, and really it was running through all these calculations. Since I'm done with that calculation, I am going to actually check that answer. I feel like I should. It's good for me to do. Mr. Duncan, would it be possible for you to post these blank questions on the classroom? Of course, that's fine, Hiba. I will do that as soon as I'm finished. And I'll be done in literally 2 minutes. I got my answer from physics and maths tutor. I got these questions in particular. So I want to show you the walkthrough of how I found them. So I went to physics and maths tutor. I went to science. I went to chemistry, and I went to chemistry revision. I then went to edXL GCSE. And I went to inorganic chemistry. I went to acid-base questions number 1. Let's have a look at the mark scheme. Right, and this was right at the end. Let's check my answer. The answer's really thrown me off. I don't like it. I'm out by a factor of 10. I knew I was going to be. What have I done? Guys, that's very interesting. I knew I was going to be out. Where have I gone wrong? So the first one was 4 times 10 to the minus 4, which makes sense. I've got it. There's the grams. What have I done? I knew that I'd made an error because it didn't make any sense for it to be that low. What have I gone and done? So 4 times 10 to the minus 4, that is correct. 1, 2, 3, 4. I've got a calculator. I love being able to do this on a calculator. 0.0004. If I click S to D, which is not on this calculator, what a night. I've got a funny calculator here from a teacher, equals. I don't know how to convert that to S to, where's eng? Oh, hang on a sec. Hang on, shift eng. No, that didn't work. Eng equals. Oh, good grief. It won't let me go back again now. Calculator not being particularly useful there. 400 times 10 to the minus 6. Do we need an account for that site? Tell me, I'll do it. No, you don't. It's totally free. Totally free, Ange. So where have I gone wrong? 0.004. 0.0004. That is 4 times 10 to the minus 4. That is correct. Go to my mark scheme. That is correct. There you go. 1 and 2. Yeah? Next, times by 5. I did that, which gives me 2 times 10 to the minus 3. I got that. That's there. 2 times 10 to the minus 3. Next, I then times it by 10. What did I get? I got 2 times 10 to the minus 2. I got that as well. So how it does 2 times 152 get me, what have I done on my calculator, guys? That calculation should have given 0.002 times 152. What? I have no idea guys, I have no idea how I did that. What I did on my calculator, but that was a calculator error right there. I don't know how it was I even did it twice. And again, I don't know whether or not it was missing, whether I pressed a point or something, but my calculator literally gave me, I don't know why. I have no idea how I did that. Everything was right, and I noticed that the math seemed really tiny. I knew that there was an error. That's the whole idea. I said to you guys last lesson, I'm trying to I had a student gave me some feedback once, which was, is it possible for you to try and convey the understanding and how you recognize when numbers are incorrect? Because you seem to do it you do it so easily, and I don't quite understand how you're doing that. And I did know it was wrong because iron 2 sulfate, like that's heavy. It's got an MR of 152 and water weighs 18, and that's 5.5 grams. It's gonna be most of it. So when I got 0.304 grams, I was like, that does not look right. So at this point, I will leave you guys be. I will post questions on the classroom for you guys to do. Ending tomorrow. Let's see if I can bring this back. Hey guys. Right. This brings me to the end of my webinar. I hope you guys understood the calculations. If you want to, you can consider them on a very stepwise basis. We work out moles of the solution that we've put in using our pipette. Wait, you're in school. Yes, I am, Julian, in school indeed. So you work out the moles of the stuff that's going into the conical flask. You look at the volume from the burette and the concentration of what went into the burette, and you're using that mole ratio in between. So it goes moles, mole ratio, moles, and then you're done. It's not a difficult process. It's the same that we always run. It's very straightforward. If you have any difficulties, I'll post some questions. There's haze. No, that's probably because my camera's got dust on it. Guys, I will see you next lesson. Hopefully it'll be in school. I'll see you soon, guys. All right. Have a nice weekend. See you later.